eigenvalue problems for ODEs. Well, some boundary value problems for partial differential equations that are amenable to analytic techniques. So, for example, constant coefficient second order linear equations that are called heat wave and potential, and are solved with some type of Fourier series representation, and that's obtained from the Sturm-Liouville eigenvalue problem, ODEs, that arise when you separate variables. So, Maple has the ability to solve analytically some of these partial differential equations. But when you get down to looking at the Sturm-Liouville eigenvalue problem, we find that Maple doesn't do an immediate job on those. You have to help Maple along. So the role of Maple in the solution of these Sturm-Liouville problems is going to be the subject of this webinar. So we'll look at some techniques for separating variables and how you can guide Maple to the solution of the resulting Sturm-Liouville eigenvalue problem will be shown. Now, this is the third edition of a May 2007 Tips and Techniques article, written eventually in Maple 11. And it necessarily made use or ample use of Maple commands. Now, this recasting is an amplification presented in a predominantly syntax-free mode. So we're going to initialize Maple so that we can more efficiently work these problems. And I brought up here the typesetting rules. I think it's an assistant. Tools, assistants. No, it's in the view menu. Typesetting rules. And I'm looking at this section right here. Dependency suppression. And you will see here an image of what that looks like. What I want is x of x and t of t to show up as just an x and a t, capital letters. So this is the remove section. This is where you enter stuff. So you would type in this, x of x, and click add function. And then you would type in t of t and click this button here. This is to remove the dependency suppression. And this shows you what prime and dot notation for derivatives will look like. And then there was a done button in the lower right-hand corner. You'd have to press that to finish the job. That is equivalent to running these two commands. I just thought I would write these commands here for you to see what's really happening. So it's a typesetting operation. I am suppressing the dependency display in x of x, t of t. And this is talking here about primes are derivatives with respect to x, and dots over dots are derivatives with respect to t. Now let's look at what Maple does with a partial differential equation. The dsolve command applied to here this wave equation, constant out front, simple boundary conditions, endpoints fixed on a finite piece of string, initial distribution of the displacements, no velocity, no initial velocity imparted. The dsolve command produces this solution. It computes the eigenvalues and it computes the eigenfunctions, and it writes down what the Fourier coefficients look like. Does that for a partial differential equation. Now, if you want to see the command hiding behind here that did this, I'll show you this once because it's a device I use a lot. Hide the input behind the cell in which the output appears. So go up here to Format, Table, Properties. And here, if you click this button to show input, you'll see behind what generates this output. And I use this module structure to hide or protect any local variables I might have to use so that later on I don't get into conflicts. And so now the next thing I want to do is look at how to separate variables and obtain solutions such as this. So now let's walk Maple through this classic steps of separating variables, getting the Sturm-Liouville eigenvalue problem, and so forth. So here's the partial differential equation. It's that wave equation. I use the context panel to assign this a name. Product solution x of x, t of t. Assign that the name. Evaluation template from expression palette. I'll show you that once here. We've got all these palettes. Expression palette. You'll see signing. It's this one right here. It's assigning. It's the eval command hidden in an icon. Okay, so U in the partial differential equation is this capital U. That's the name I gave the product solution. I take the resulting equation here, two dots over dots differentiation with respect to t, primes differentiation with respect to x. You'll notice that the independent variables have been suppressed. Take that and divide by the solution, but I throw in the c squared besides because I want the c squared with the t equation. And now I have a function of t equal to a function of x. The only way that that can happen is if both of these are equal to the same constant. And when I teach that to students, or when I taught that to students, I would have one student give me a function of t and a different student give me a function of x, and then I would ask the class, how do we make these two things equal? Can it be possibly made equal for all values of x and t? And then they realize, okay, that's why you make it a constant. Okay, so now this has an equation label, and what I'm going to do is I'm going to reference that equation. Over here, I'm going to deal with the t equation. Over here, I'm going to deal with the x equation. So I grab the left-hand side, and I multiply through by that denominator after having set that left-hand side equal to lambda. And so now if I take this and bring everything to the left side, I've got the t equation. Do the same thing for the x equation. Grab the right-hand side, set it equal to lambda, multiply through by x, bring everything over to the left, and now I have the x equation. This is the one that's going to give me the eigenvalues and eigenfunctions. And how do I get that? That's when I apply the boundary conditions to the assumed solution, and it tells me that x of 0 and x of pi have to be 0. So now we want to tackle solving this Sturm-Liouville eigenvalue problem. Solve the DE. So if you apply dsolve to this equation with these boundary conditions, Maple will come back and say x is the 0 solution. Dsolve will not do anything like what pdsolve did for the partial differential equation. And that's why you have to adroitly intervene. So you've got to take this equation in steps. First of all, you want to get the general solution of this thing without the boundary conditions. You want to find out, are there values of lambda for which the characteristic equation has a multiple root? Because that solution, that general solution, is different from the general solution where you have two different roots and one does not morph into the other. Then you apply the boundary conditions to these general solutions and you see what the resulting homogeneous equations are. If you put them in a matrix form and you take the determinant, set that equal to 0, you'll have an equation from which you can extract the eigenvalues, because those will be the values that make that determinant 0, so that the coefficients are not both 0. And from that you get the eigenfunctions. So let's take the case where you have either Dirichlet conditions or Neumann conditions, both homogeneous. Let's take a look at this Sturm-Liouville problem with homogeneous Dirichlet boundary conditions. So you want a general solution, so you make the exponential guess, plug it into the differential equation, you get solutions for m, and it turns out to be plus or minus lambda. That tells you that lambda equals 0 is the double root case. And in that case, the general solution will be a polynomial. So now let's do the double root case. So take the differential equation, set lambda equal to 0. There is the equation now. It's x double prime equals 0. The solution is this polynomial. And you can argue right from here that this is a straight line if you graphed it. And a straight line is not going to be 0 at each end unless the straight line is 0. You can see this little note here. It's tempting to assign this as a function, but that would then corrupt the meaning of this letter x, so we don't do that. So to show that lambda equals 0 is truly not an eigenvalue, we do this. We type s of x. That's what we're going to call this thing now. Not x, but s of x equal to this polynomial expression. And we make that a function. So we can do s of 0, s of pi, get these two equations. If you solve them, you get the two constants, c1 and c2 equals 0. That says the eigenfunction associated with lambda equals 0 is the 0 function. Therefore, it's not an eigenvalue. Lambda equals 0 is not an eigenvalue. And next is to take the case where lambda is not 0. Now we want to take the general case, lambda not equal to 0. Get the eigenfunctions, if we can, eigenvalues and eigenfunctions. I want to use this letter s again, so I unassign its value. Then I recall the differential equation, hit it with a solve the differential equation using the context panel. Here is the solution. This is the way Maple presents the solution. I only want this right-hand side, so I grab the right-hand side. And that's what I now want to call s of x, because x will become 0, x will become pi, and it's just easier to have that as a function. In order to obtain the eigenvalues, and ultimately the eigenfunctions, we need some tools from linear algebra. So here I've loaded the student linear algebra package, and here are the steps I'm going to perform. I'm going to apply the boundary conditions to the solution, this general solution that we obtained here called S. So we get two homogeneous equations. I put them into matrix form. This is the right-hand side. I'm looking for these constants C1 and C2. In order for them to be non-trivial and non-trivial solutions, the determinant of this matrix has to be 0 because these are homogeneous equations. So I grab this. There's the matrix whose determinant I want. There's the determinant. I set this equal to 0, which Maplesoft command assumes, and solve for lambda. And this symbol, underscore C2 stands for an integer. So minus n squared. So lambda equals minus n squared for integer n are the eigenvalues. And clearly I can just take n positive. Okay, now that we know the eigenvalues, we can move on to the computation of the eigenfunctions. All right, so here is the solution. We called it S. We make lambda be minus n squared. This is what it's going to look like. We do a simplify with the option assuming positive, and clearly this minus comes out. That's what the capital I represents square root of minus 1. Put it in rectangular form, a plus bi form. It needs some cleaning up. We need to collect the cosine terms. We need to collect the sine terms. It's a factoring operation. So when you go to the context panel and select collect, you get this dialog box opens. You have a drop down. You collect with respect to sine. Then you have to go back and collect with respect to cosine. And so finally you get the general solution in this form. The question is, what happens when you apply the boundary conditions to this form? Okay, so now we want to apply the boundary conditions to this solution. It's got equation label 21. So here I set x equals 0, and here I set x equals pi. I have these two equations to solve. This one says C1 plus C2 is 0. That knocks out the cosine term. Sine n pi is 0 for each n. So this difference of constants times I remains arbitrary. And so you conclude that you have multiples of sine nx. And interestingly enough, now that you know what the eigenvalues are exactly, you can solve the ensuing differential equation with lambda equals minus n squared. Apply the boundary conditions, but you do need assuming n is a positive integer. And you can't do a solution in a dsolve solution in a syntax-free manner and similarly apply this assumption. So I typed out the command, and you can see that you get a multiple of sine nx. So now let's try some of these same processes. Homogeneous Neumann conditions imposed. So we know that this linear function is a solution of the differential equation x double prime equals 0. So if you apply the homogeneous Neumann conditions, you're going to get that one constant is 0 and the other one is free. So that tells you lambda equals 0 now is an eigenvalue, and the eigenfunction is 1 because it's this constant. So now the general case, lambda not equal to 0, s of x is still the general solution. So here we get the two equations, s prime at 0 is 0 and s prime at pi is 0. So I have these two equations. So here they are together as a sequence. Put them in a matrix form. These are the coefficients. This is the right-hand side. These are homogeneous equations. The determinant needs determinant of this matrix. Here is the determinant. You set it equal to 0, which is what the solve command will do. And it says, okay, the solution is lambda equals 0, which we've already dealt with. And lambda is minus n squared, because this is an integer. Well, we have the eigenvalues. Now it's on to the eigenfunctions. So this is the general solution. We let lambda be minus n squared. We get this expression. Simplify assuming positive. The minus sign comes out as an I. Put it in rectangular form. We do a collect. We get collected on sine. Did not collect on cosine. I know I have to differentiate this in order to apply the boundary conditions. So here is the derivative. Got equation 35. So I take equation 35 and I evaluate it at x equals 0. and x equals pi to get these two equations. Well, Maple simplifies when I say assuming integer. It knows that sine n pi will be 0. That drops out. It knows that cosine n pi is minus 1 to the n. Depending on n is positive or negative, it's plus or minus 1. So we are looking at this expression. Well, n is not 0. Minus 1 to the n is not 0. So this must be 0. So go back here to the expression, not the derivative, but the actual expression for the solution. This term will drop out. The sine term will now drop out. Cosine term will survive, and it's a C1 plus C2. It's a multiple of cosine. And if you take the differential equation and you put for lambda minus n squared and the boundary conditions and do a dsolve assuming that n is a positive integer, you get that the solution is a multiple of the cosine, which is the eigenfunction for the homogeneous Neumann condition. In an attempt to see how robust these procedures are, I picked a differential equation that was not formally self-adjoint, stuck in this 2y prime term. Then I also upped the scale on the boundary conditions. These are separated boundary conditions, but you have y prime at 0, y at 0, y prime at pi, y at pi, homogeneous. So following the same set of steps, we want to get the characteristic equation, so we make the exponential guess. Here is your characteristic equation. You solve for m, and you notice that if lambda equals 1, this drops out, and you have a double root, m equals minus 1, for which the solution is then e to the minus x. You have once and twice. The second time you put the x in front of it. And it is to this solution that you apply the boundary conditions to see if lambda equals 1 is an eigenvalue. So how did we proceed to do that? Well, I unassigned s, so I could use it to assign s of x as a function to this expression. Then I typed the boundary conditions. S prime now makes sense to Maple. S at 0, S prime at 0, S at 0, S prime at pi, S at pi. I get these two equations, put them in a matrix, a vector form, grab the matrix, get its determinant, and you can see e to the minus pi, e to the minus pi with a pi. This is never going to be 0. So lambda equals 1 is not an eigenvalue. Now we want to get those eigenvalues that are not equal to 1. And I'm anticipating here that I'm going to make use of the roots command, because we're going to have to get these eigenvalues numerically. So I load the Student Calculus 1 package, and then the rest of the stuff is pretty much the same. Unassign s and let s be the general solution, where you have these two exponentials, minus 1 plus or minus the square root of 1 minus lambda times an x, a and a b. And I have to apply the boundary conditions, which is what I do here. Same step that I did up above. S prime at 0, S at 0, S prime at pi, S at pi. Get these two equations. And you notice they're getting rather longer now. Put them in a matrix. Grab the matrix. Get its determinant. I hit it with a simplify. It's a little bit smaller. And I'm looking at these lambdas under the square root and lambdas in the exponential. There's no way I'm going to get an exact solution to this. So I switched to numeric computations. And the simplest way to get the zeros of this expression is to use the roots command. And that's what I put up in here. I want I fiddle with this and you find out. Take the range from 0 to 26, and I calculate numerically, and this pops up when you use the context panel, and Maple returns these values for the roots that it found. You notice this last one is 25 point something. That's why I went out to 26. But there is this 1 in here. We've dealt with that case. Don't want that one here. So I give this a name, temp. And I remove from temp this second member. That's what this temp2 is. It's this second member. And so this now is the list of eigenvalues that I want to deal with. I've had to compute them numerically, and I call this capital lambda. So now we've got this first eigenvalue. It's less than 1. The next one is greater than 1. Now look down here at this square root that appears. When lambda is less than 1, this is real. But when it's greater than 1, as all these will be, this is complex. So that has implications for finding the eigenfunctions. So to find the eigenfunctions, we're going to have to treat these two cases separately and be careful what we do. So let's get the eigenfunction corresponding to this first lambda, which is less than 1. And I'm going to just take one of the boundary conditions. I'll take the first one. So here's that boundary condition, s prime at 0, s at 0. Here it is. This can be isolated for a. So I get a in terms of b. If I put that back into the solution, I get this expression. And you have b here, b here, b here. The eigenfunction is determined up to an arbitrary multiple. So why don't I set b equal to 1, which is what I do here. Set b equal to 1. And this is the expression for the eigenfunction corresponding to this 0.455 when I set that to lambda. Now we know how to get the eigenfunction for that first lambda, 0.455. Lambda is less than 1. You use this expression. We put that value in for lambda. But you can also use this for lambda greater than 1. But now you're going to have complex numbers showing up. That would mean you'd have a real part and an imaginary part. And they both can't be solutions because they can't have these two different independent solutions. So they got to be proportional. So I'm going to take the real part. I'm going to take the real part under the assumption that lambda is greater than 1. So I get this as the real part. And I'm going to switch to explicit commands because they're a little bit more efficient. Collect option only collects one function at a time. If you use the command, you can put a list of functions you want to collect against. It's more efficient. So this is the real part in a more simplified form. Now I want to do a loop that prints out the first 5 eigenfunctions. So here's the first one. You take that expression 42 over here, up here, and you put in lambda equals the first member of that list of eigenvalues. And the remaining 4, you put it into this expression. And you get these 4 eigenfunctions. And if you draw a graph of those first 5 eigenfunctions, and these first 5 eigenfunctions graphed look like this. They seem to have the interlocking of zeros that a Sturm-Liouville problem has. This is not a Sturm-Liouville problem because it's not self-joint, but these look good to me. Now Maple has some tools that will allow us to double check what we just did. And surprisingly, it's in the dsolve command, because the dsolve command can compute eigenpairs numerically. So let's set that up. Differential equation, first and second boundary conditions. And let's group the differential equation, the 2 boundary conditions, and one arbitrarily written algebraic equation, because there is this parameter lambda that we don't know, and Maple doesn't know. So it needs one more piece of information to deal with this parameter, because it's going to work numerically. And so let's call this whole thing sys, and we'll give that to the dsolve command. And then down here in table 2, I'll show you what happens with the dsolve command. Now down here in table 2, I list eigenpairs. Bit cryptic until I explain to you what Q looks like. So dsolve is system numerically. And this is the first eigenvalue. Remember this 0.4558? This is the evaluation command. I'm evaluating lambda because Maple computes lambda as part of this numeric process. And I'm evaluating it at Q1 of 0. And if you don't see what Q1 looks like, you don't know what that means, and I'll show you that momentarily. Second eigenpair. You've got to give Maple a hint as to what an approximate solution might look like. And here you're guessing. And so it's almost like you need to know what the eigenfunctions are before you can solve the problem and get the eigenfunction. But you've got to approximate or give an approximate value for lambda. The next eigenpair, you've got to do the same thing. You've got to give an approximate solution. So you're guessing, but the more you know about the behavior of these systems, the better your guess will be. Second eigenvalue. Notice it comes out 1.1. Third is 4.243. Should we go back and look at those eigenvalues? Where is that lambda? Way back here. 4.243. 4.243. I'm just disappointed in this one. So let's take a look at this Q thing. Q is a collection of procedures that Maple constructs so that when they're implemented, they do the computations. You can evaluate one of these Qs at a value of x. If you put in 0.1, that's the first thing that gets placed in this list, value of x. This is the value of y that would correspond. This is the value of y prime that would correspond. And this is the value of lambda. So here, it doesn't make any difference what value you place for the x, because you're going to compute the same lambda no matter what value you put in here for that particular Q. When I evaluate lambda at this list of numbers, Maple matches the lambda and it picks this out, and that's why you get the eigenvalue out here. Well, with that clarified, here's a graph of those three functions that I computed numerically. They tend to match these. I did not do an exact match, but that's how you would use one tool to corroborate the results of another tool. So now I dug up an actual Sturm-Liouville boundary value problem. Here is the equation, and here are the separated boundary conditions, homogeneous. Let's initialize Maple so that we can solve this problem. You see, I began with a restart to clean up everything, and then I loaded these three packages: linear algebra, calculus 1, and the plots package. Here's the equation. I give it the name DE. boundary condition number 1, boundary condition number 2. Then down here, I used a command to do a typesetting rule. What will happen is that the Bessel function, instead of appearing as Bessel J, will appear as the letter J. Bessel Y will appear as the letter Y. And I've shown you at the beginning how you can do that with the typeset rule assistant. So I won't do that again here. So here's a syntax-free solution to this problem. Differential equation echoes back. Context panel, solve the DE. You get this solution. So the Bessel function J1 and Y1. And I assign this as a function, so now Y is this as a function. Apply the boundary conditions. Here are the two boundary conditions. Now the boundary conditions had the letter Y at 0, Y prime at 0. Maple understands that notation. It writes the two boundary conditions. Here's the first one. It ends at this comma. Here's the second one. Put it in matrix form. It's kind of messy. Grab the matrix and I get its determinant. There's no way you're going to get an exact solution for lambda, so I hit it with the roots command from calculus 1, and I do that through the context panel. Here are the first 1, 2, 3, 4, 5 eigenvalues. So that's why up here I show you that I went from 0 to 100, and I calculated numerically using that calculus 1 roots command. And I give that the name lambda, capital lambda. So let's find at least the first eigenfunction corresponding to this first eigenvalue. So how do we do that? Well, here's what we did before. We took one boundary condition. I took the first one. This is what it looks like. Evaluate at a point lambda equals lambda 1. So these lambdas in here will be set equal to the first lambda in this list. And so all of this collapsed to this numeric expression. And what we did before, we solved for one constant in terms of the other, then put it back in here. And so everything is now multiplied by C2, which I can arbitrarily set equal to 1, and that's what I've done here. So if I evaluate this now at lambda equals lambda 1, then I get an eigenfunction. And here is its graph. So the steps that we performed earlier work here, and we could continue and we could cross-check with dsolve, numeric, and so forth. But at least I verified for my own satisfaction that the steps that I've put together do seem to carry through and work. And actually now one more problem, Sturm-Liouville problem. I'll do it with commands, and you can see it's a little bit more efficient than it is with context menu, context panel stuff. Restart, I'll get a clear start. I'm going to use the linear algebra package. I define a function p. Here it's py prime prime. That is a formally self-adjoint differential equation. These simple boundary conditions will give us a self-adjoint boundary value problem. I'm going to use dsolve to get the general solution. No boundary conditions here, just a general solution. Grab the right-hand side and use unapply to make a function. And the name of the function is capital Y, and it's a little trick to make it echo y of x equals, and you have two constants of integration. Now we'd like to get the eigenvalues. So we do what we did before. we apply the boundary conditions. Well, they're simple enough to type in here. I generate a matrix using the generate matrix command. These are the constants. By saying augmented equals false, I get directly the matrix. I get its determinant. And you'll notice that I didn't do anything fancy to make Bessel functions appear as just the letter J. So it says Bessel, 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 Bessel. Apply the roots command from Student Calculus 1. D is the expression, so D equals 0 is what I'm solving. And I want lambda to go from 0 to 45, which I found out by experiment gives me the first 5 eigenvalues. Well, now that we have eigenvalues, let's see if we can get at least the first eigenfunction. So how do we do that? We take one of the boundary conditions, y is 0, and we put in lambda equals the first eigenvalue. Then we isolate one of these constants in terms of the other. I did C2 in terms of C1, and put it back into the general solution. So we have a C1 here and a C1 here. Now, instead of just setting C1 arbitrarily equal to 1, I said, let me try normalizing it L2 style. So I put lambda equals lambda 1 into y1. That's this guy. Square and integrate. Set that equal to 1, and I solve for the values of C1. Well, I picked C1 equals the negative value. So I plug that in here into the general solution. This is what it looks like for that first eigenvalue. I draw a graph. That's what it looks like. Well, it's always nice when you can cross-check by using a different tool and see if you get the same result. So here's a numeric corroboration using dsolve numeric. Remember how to do that? Differential equation, boundary conditions, and an extra condition that you make up so that y prime at 0 equals 1 allows Maple to compute that unknown lambda. It creates a list of procedures which, when evaluated at a point, give you numbers. So here I've taken t, this t here, at 0. So it says that you've evaluated at x equals 0. This is the corresponding y value. Here's the derivative value. And this is the lambda. 1637. And we'll go back up here. Where did we get that? This stuff here. 163709. That's pretty much what we computed here. 9. The red graph is this one. The green graph is the eigenfunction that Maple calculated numerically. They're not the same. The scaling is not the same. So I asked the developer who wrote this code if there is any attempt to scale this solution, this numeric solution. And he said no. So the scaling that I picked up here, this L2 scaling that I picked up here, totally arbitrary on my part. I don't know what the scaling is here because the developer says no attempt was made to scale that solution. So one scaling that you pick is as good as another. But I deliberately put this here so that you can see that the scaling is essentially either you can call it unknown or arbitrary. But final bottom line here is the set of tools that we put together, they seem to work. You can make a lot of progress either with commands or with point and click syntax-free techniques.